Hey everyone, welcome to this explainer. Managing a building's thermal envelope, it goes way beyond just dreading that monthly utility bill. It's actually a constant, literal battle against the physics of heat loss. When conduction, convection, and radiation are all ganging up on your structure, your internal energy loads are going to absolutely skyrocket. Today, we're diving deep into thermal efficiency, a guide to building insulation materials. Because if you're seriously analyzing what's hiding inside your walls to optimize performance, you already know that making the exact right material choice for the right environment is absolutely crucial. So let's jump right in. Here's our quick roadmap for today's explainer. We'll start by defining thermal efficiency, then we'll meet our insulation materials, put them through a head-to-head comparison, and finally, wrap things up with our final verdict. All right, moving right into part one, defining thermal efficiency. So what exactly is thermal efficiency when it comes to building insulation? Fundamentally, it's just measuring resistance to heat flow. Think of it like putting a really good, heavy winter coat on your house to protect it against the bitter cold. We're dealing with the core mechanics of thermodynamics here: conduction through solid materials, convection through moving air, and radiant heat transfer. A high-performance building envelope acts like that perfect winter coat, effectively shutting down all three of those pathways. And when we talk about optimizing this, we aren't just adding random bulk to a wall. We're looking at how well a continuous insulation layer stops thermal bridging. You know, those highly conductive pathways that run right through your studs and framing, leaking heat like a sieve. We want to stop those while also managing moisture and air infiltration. The ultimate goal? A tightly sealed structural envelope where your internal temps stay completely stable no matter what crazy weather is happening outside. Okay, let's shift gears to section 2, meet the insulation materials. Time to introduce the heavyweights. When we look at the primary materials used to actually build these protective envelopes, we basically categorize them by their material science and industry track record. In corner number 1, we have the legacy heavyweight, fiberglass. This stuff has been the absolute standard for decades, and honestly, it's still everywhere. Next up, the sustainable challenger that's really gaining traction in high-performance builds, cellulose. This is a super cool material that actively repurposes recycled paper products treated with borates. And finally, the modern marvels, synthetic barriers, specifically closed-cell and open-cell spray foam. Each of these contenders brings distinctly different physical properties to the job site, and understanding how they behave mechanically is exactly how you choose the right tool for the job. Let's put these into perspective. Traditional fiberglass, it operates as a straightforward, permeable batten. It's the tried-and-true workhorse that excels in standard, easily accessible wall cavities and wide-open attics. But because it's pretty low density, it's highly susceptible to air movement, meaning you almost always need to carefully install a separate vapor barrier to keep moisture in check. Contrast that with spray foam, the high-tech modern diva of the insulation world. Since it's applied as a liquid, it physically expands to perfectly fill complex, weird architectural geometries. It naturally seals up bypasses and acts as its own integrated air and vapor barrier all in one. Now sure, it demands precise, climate-controlled professional application. You can't just slap it up there, but the payoff is a highly rigid, continuous monolithic seal that traditional fiberglass just literally can't achieve on its own. Which brings us right into section 3, the head-to-head material comparison. Let's look at the data. Now, what's really fascinating here is looking at the holistic trade-offs. As you can see, it's a massive balancing act between thermal resistance, your project budget, and insulation complexity. Spray foam absolutely delivers massive R value and top-tier air sealing, but yeah, it's going to command a premium price tag and absolutely requires a specialized pro to install it. On the flip side, fiberglass trades that sky-high thermal resistance per inch for incredible affordability and ease of handling. It's a total staple for wide-scale deployment where you have plenty of cavity depths to work with. And then cellulose sits in this really strategic middle ground. It offers slightly better air-blocking properties than fiberglass while still being highly cost-effective, though you'll usually need pneumatic blower equipment to get that proper dense pack compression. Just look at this chart. It brilliantly illustrates the raw stopping power of these materials. If we are focusing strictly on pure thermal resistance per inch, closed-cell spray foam is the undisputed champion. That performance comes from its dense cellular structure, which basically stops conductive heat transfer dead in its tracks, way better than fibrous materials can. So if you're dealing with a constrained space, like shallow 2x4 framing or an unvented roof deck where you need maximum R value in a tiny footprint, spray foam is a no-brainer. Cellulose, again, holds a very solid, respectable middle ground here, especially when densely packed. Meanwhile, standard fiberglass comes in with the lowest thermal resistance per inch. But hey, don't count it out. In places where volumetric space is basically unlimited, like a huge, deep attic floor, you can achieve a highly effective total thermal barrier just by piling on more depth, really taking advantage of that ultra-low cost per square foot.
All right, we've reached section 4, the final verdict.
Here's the most crucial takeaway from all this. Maximizing overall thermal efficiency is never, ever just about throwing money at the most expensive material. It's really like a giant puzzle where you're matching the precise properties of the insulation to the specific environmental demands of the space. Optimizing a building's energy profile requires total systemic harmony within the envelope. For example, a really high-performance home might strategically use closed-cell spray foam up in the roof deck to fight off intense radiant heat and stop air leaks, but then it might simultaneously use cost-effective blown-in cellulose in those deep attic flats, and maybe even rigid mineral wool on the exterior to break up structural thermal bridging. The whole shebang has to work together as a comprehensive, integrated system tailored specifically to your structure's unique load requirements.
So I'll leave you with this question to chew on. Is your own building's thermal envelope truly optimized for maximum efficiency and savings? It is absolutely worth taking a hard look at the specific microclimates within your own architecture. Ask yourself, are you relying on highly permeable, old-school materials in tricky, moisture-prone spaces where modern barriers are now the standard? Are hidden thermal bridges quietly compromising your well-insulated wall cavities? By properly diagnosing the structural integrity of your building's envelope and bringing the right material science into the right zones, you can fundamentally transform how your structure performs for decades to come. Thanks so much for joining me for this explainer, and I can't wait to see how you leverage this data to lower those utility bills on your next project.